We now concentrate, in isolation, on the performance effects achieved by the new SEMAFOUR developed multi-layer LTE Wi-Fi traffic steering SON functions. In order to do this, we will first address the baseline scenario without traffic steering. In the baseline scenario, which serves as a reference, users are automatically served by the strongest Wi-Fi access point, provided that the received signal strength index, RSSI for short, exceeds -92 dBm, and hence the user is indeed within Wi-Fi coverage. This access network selection is made regardless of the respective loads on the candidate Wi-Fi and LTE cells, and hence regardless of the achievable performance. Let us now zoom into the most interesting area in Hanover for this scenario by clicking the TS button on the network panel. This brings a demonstrator view to the dense urban environment in the center of Hanover, characterized by highly variable propagation conditions, a high traffic density, and accordingly a dense deployment of LTE sites and Wi-Fi access points. On the network panel, we see three distinct types of cells, namely 4 sectorized LTE microsites, as well as 28 collocated omnidirectional LTE microsites and Wi-Fi access points installed at lampposts. As before, the LTE microcells and Wi-Fi access points are depicted as concentric circles, which in the current configuration are colored to show the respective cell loads. Recall that the inner and outer disks correspond with the LTE microcell and Wi-Fi access points respectively. Looking at the best server areas, we observe that, as expected, these best server areas are fixed and simply cover the region where Wi-Fi provides coverage, regardless of whether Wi-Fi provides the best performance throughout the covered area. Turning to the KPI panel, we see 4 distinct charts showing different metrics that are relevant for the traffic steering scenario. The top chart shows a fraction of users served by the LTE and Wi-Fi technology respectively. As expected, in this baseline scenario where a user selects Wi-Fi if coverage is available, we see that indeed a relatively high fraction of users, about 80%, is served by Wi-Fi access points. In line with this, both throughput charts, whether considering an average user throughput or the 10th user throughput percentile, separately per radio access network and also in an aggregated sense, show that the relatively large number of users served by Wi-Fi technology results in relatively low throughput values compared to what is experienced in the LTE network. This scenario illustrates well the need for LTE Wi-Fi traffic steering, in that it exposes the potential performance enhancement that can be achieved by intelligently offloading traffic from the Wi-Fi to the LTE network. The final chart displays a fraction of the LTE and Wi-Fi cells which experience overload, meaning that the average utilization of the cell's resources exceeds a given threshold. This chart clearly exposes both the congestion in the Wi-Fi network and, indirectly, the underutilization of the LTE resources. Let us utilize the current demonstration scenario also to exhibit another feature of the SEMAFOUR Demonstrator, as briefly introduced before, namely the emulation of the end-user performance of a video streaming session as experienced on a handheld device. The demonstrator supports 2 distinct ways of showing this end-user performance. One option is to select an individual user on the network panel and map its individual time-varying performance to a handheld device. Alternatively, we may select a given user throughput percentile curve on the KPI panel and apply those statistics to emulate the video stream and display it on the handheld device. In the latter case, if we for instance select the curve showing the overall 10th user throughput percentile, the emulated video stream would show the service quality experienced by at least 90% of the users in the network. For the current demonstration, let us choose the second option and indeed opt for the 10th throughput percentile curve. We now see a video stream generated by a person walking through Hanover, and note that the experienced video quality is rather low. This is due to the fact that most users in this scenario are served by highly congested Wi-Fi access points and thus experience relatively low throughputs and high packet delays. At a later stage, we will revisit this feature and show how the experienced video quality is improved by the traffic steering SON function as desired. Let us now see what happens if we select and deploy one of the available traffic steering SON functions on the operator panel. In this demonstration scenario, we opt for the so-called TS-IRAP algorithm. Shifting to the next day activates the SON function, and we can right away observe on the network panel how the best server areas now vary over time. What the selected load-based LTE Wi-Fi traffic steering SON function does is that it dynamically adapts the cell-specific thresholds for the RSSI, which directly influences the access network selection. More precisely, only users measuring a Wi-Fi beacon stronger than this RSSI threshold select Wi-Fi as their serving network technology. Hence, the lower the threshold, the larger the effective Wi-Fi service area, and hence the more traffic is offloaded to the Wi-Fi network. The objective of the SON function is to enhance end-user performance by an efficient utilization of both LTE and Wi-Fi resources. Let's right-click on one of the Wi-Fi access points in order to open the cell view panel. As before, the cell view panel shows the area immediately surrounding the selected cell, again showing the time-varying service areas of the cells that are also visible on the network panel. Notice that in this multi-rat setting, the notion of best server area loosely departs from its traditional interpretation. While the latter is purely based on pilot signal quality, in the current scenario it indicates the chosen service area from a best throughput performance perspective. We now configure the two available charts on the cell view panel to show the correlation between the key monitoring KPI and control parameter. In the control parameters chart, we select the RSSI threshold, while in the KPI chart we show the average resource utilization, which expresses the load of the Wi-Fi cell. If we carefully observe the parallel evolution of these two metrics, we see that the SON function indeed decides to raise the RSSI threshold after observing a high load, while it lowers the threshold at times of low cell load. We also see how the load measure responds to the control parameter change as intended, in the sense that, for instance, an increase of the RSSI threshold indeed offloads traffic from the Wi-Fi cell to neighboring LTE cells and hence reduces the Wi-Fi cell load. Turning to the KPI panel, we observe that indeed the SON function affects the displayed KPIs as desired. The fraction of users served by the two radio access technologies is now nicely balanced compared to the baseline scenario without LTE Wi-Fi traffic steering. This load balancing effect also affects the user throughput performance as intended, in that the user throughput experienced by Wi-Fi users has increased significantly, albeit at the cost of an unavoidable reduction of the LTE user throughput. The bottom line is visible in the overall user throughput metrics, which are clearly enhanced in comparison with the baseline scenario. Lastly, we see that the resources are now more efficiently utilized, as seen from the lower fraction of overloaded cells. To wrap up the LTE Wi-Fi traffic steering scenario, let us revisit the demonstrator feature that enables the display of an emulated video stream on a handheld device. As before, we select the 10th user throughput percentile curve on the KPI panel and map this to a handheld device. As expected and in line with the improved user throughput statistics, we now see that indeed the video quality experienced by at least 90% of the users in a dense urban environment in the center of Hanover is significantly better than that which was seen for the baseline scenario without self-optimized traffic steering.